I remember the Monday before MIT shut down for COVID. Or no, that wasn't. Well, maybe it was. Maybe it was the Tuesday. MIT shut down on Wednesday in March of 2020 or whatever. And I shut down on Tuesday. I said, no, I didn't know what MIT was going to do. But I said, and they sent everybody home a week later. Okay? But the Jeffrey Epstein thing was big in there.
Oh, yeah.
Okay. And I think one of the students asked me what I thought about that. I said, well, look, I'm not involved in the administration anymore. I don't know anything about Jeffrey Epstein. But I can tell you a number of stories about money talks at MIT. I put together a lecture on these stories about why the venture capitalists are always around here, and what they're doing, and how they're taking advantage of MIT's name. And it turns out I had another guy here, an alum who become a CEO of a $4 billion chemical company. He's in my house tutor, and he basically backed me up. This is what the businesses are doing. They come in and they sell the MIT name and have an IPO on Wall Street. They walk away tens of millions of dollars, and the grandmother ends up with a worthless pension fund because a lot of it's crap.
World sucks, huh?
Well, but the one I told most of the story about was the guys who were part of the MIT technology licensing program that ended up overnight. They were both worth, these two guys were worth $30 million because that's on paper. But 3 years later, they were indicted. And Professor Sadoway and I were all excited because fortunately, MIT's name did not show up on the business page of the Boston Globe being associated when we got indicted. But any other reporter could have put MIT's name there because MIT was right in there. Let me tell you. So I said, I don't know what happened with Jeffrey Epstein, but anything bad you hear is believable. Okay? But I don't know, okay? But you get up to the top and no one, it's the same problem as police. They don't police themselves. The administration will not do anything for someone who gets out of line. Oh, that's okay. It's okay to teach your wife. We won't say that in public, but we're not going to punish you for it, right? Believe me, it's what happens. Does it happen in the industry?
What?
Does it happen in the industry?
It's interesting. I knew an engineer who had shut down a supplier. This guy showed up with an enormous yacht, and he showed up with a completely restored Austin Healey for about $100,000. And it took, I guess the supplier turned him in and said, this guy's been shaking us down. He got fired. He showed up a week later at Ford in a supervisor position like nothing happened.
Yeah. You get to high enough level.
It's weird. Robin, can you see the screen and hear us and everything?
Yeah.
I can hear the screen and I can hear Professor Baskin really well. Other people are a little muted because they're behind, but it's okay.
But everything's good. You can see the screen?
Yeah.
So I can assume I got this right for once? Okay. Wow, that was encouraging talk. Julian, did you like the Chimad conference? I saw you were in there.
Yeah, I liked it. I knew a lot of talks already.
Okay. The when was that, Tuesday?
Yeah.
So this past Tuesday was the yearly conference for the Center for Hierarchical Materials Design, Chimad. Is that right? It's this is an organization that focuses on computational materials engineering, and it started in Northwestern, so they make a big deal out of being in Chicago. And they had their yearly conference, and Chris Shute from this department actually gave a presentation at the conference, which was very interesting on frame boundary chemistry. So if you have certain species in the grain boundaries, you can actually strengthen or weaken the material. It's actually very interesting. I keep on talking about it with physics. Okay, so in our last lecture, we talked about materials, ICME, we talked about structural property performance relationships. We talked about stiffness, engineering stiffness in the material, and then trying to predict stiffness based on parameters or features of the microstructure. I meant to have this slide in the last lecture, but somehow I screwed that up, so it wasn't in there. And I wanted to go over this again just to make sure. This is an example of how you can engineer a material with a higher stiffness than it would have otherwise. And there's actually very few examples of this, but this is one I want to share with you. So we mentioned last time this ceramic called iron titanate, which is a pretty useless ceramic, kind of red and orange looking. And it has this feature about it that if you have a single crystal of this material, the B axis, the B crystallographic direction, will line up with a magnetic field. So if you have a little particle and you sort of freely suspend it so it can rotate if it wants to, and then you take that and you stick it in a magnet, it'll line up. So that's what you're seeing here. So you have this crystallographic axis, the B axis, that will line up parallel with the magnetic field. So if you have lots of particles and you can suspend them in, say, ethanol, for example, just a cheap solvent, right? And you stick this sort of suspension of these particles into a magnetic field, one axis will line up with the magnetic field. And it turns out that axis is also the stiffest axis. So you can think of oops, wrong hand. Let's screw that up, guys. It's always the right hand. If you have a crystallographic axis, right? You can think of a crystal having a cubic crystal having three different directions. A, B, C, for example, or X, Y, Z, whatever you want to call them. And you can actually have different stiffnesses in each direction. So if you had a single crystal of material, like they do for like jet engine blades, and you had that single crystal, you'd find that you have three different stiffnesses, right? So you have a different stiffness in each direction because it's a single crystal, each of the three primary directions. Just so you guys know, you can't call that Young's modulus. Young's modulus implies that the material is isotropic. Remember that. So here, if you have this material and you can stick this thing in a magnetic field, and then you can find some way to solidify it or congeal it, as it is, you actually really say. So by putting in this case, we put in acrylic monomers. You suspend these particles in ethanol, a mixture of ethanol and acrylic monomers. You stick this in a magnetic field. The catalyzed acrylic monomers will cross-link because they're polymer, right? When they cross-link, they'll sort of lock in the position of these little magnetic particles. Okay, and then if you can burn out that acrylamide, compact the material and sinter it, it's a ceramic, right? So it sinters. Then you'll have sort of a quasi-single crystal. It's not really a single crystal because it's got grains, but the grains are along because it's called a crystallographic texture. That crystallographic texture means that it has different stiffnesses in the three different directions. So there's an example where you've engineered the stiffness of the material. In this case, individual thin layers were made of these little sintered parts, or these little sintered ceramics, little crystallographic textured material. They were laminated together, and in so doing, we were able to set up a residual stress field, because not only does the Young's modulus change the direction, but also the thermal expansion. So as you cool this thing, some layers would contract faster than others, and you can engineer in residual stress fields. That part's not important, but I just want you to think of this as an example of how you can engineer the stiffness of a material. Last time, remember, we mentioned aluminum, lithium. Aluminum, lithium has a higher stiffness than just aluminum. So we went through these different examples. Clear from the conference? So this is interesting. This is lifted from Greg Olson. So this is length scale. So you're going from small to bigger, and it shows here the different models that you can use to model the behavior of the materials at different length scales. It's on the on the right side. On the left side shows different instruments or tools that you can use to understand, to measure these different properties that maybe you try to predict with these models on the right side. Okay, Olson diagram, Greg Olson. I should probably tell you that he's teaching a design and materials course in the spring semester. And if you like this sort of computational materials engineering thing and structure property performance relationships, you should take this class because it's really good. I took this class when he took it at Northwestern, when he was at Northwestern, and I learned a real lot. So very inspiring course about how to actually design materials, not just take book values. Okay.
How would you say it is for like somebody who hasn't had a whole bunch of experience in like computational materials? Because I've heard about the class and I heard it's really good,
Okay.
but I don't have much experience in computation. Only like mathematics and harder, but like that's it.
Okay. ThermoCalc is very easy to use. It's even easier to use now than it was, back when I was a grad student. It has a great graphical user interface now. It's very friendly. I'm sure you won't have any trouble with it. If you get into trouble using like ThermoCalc, just as an example, there are people on campus here who can show you how to use it. Like Clay Hauser is one of Professor Olson's grad students, who's now a grad student at MIT. And, I know he's in town. Ask for help. You might have to be a little bit proactive and stand up and say like, hey, I don't understand how to do this, or I don't understand how to do the calculation. And somehow somebody, I'm sure, will show you how to do it. Julian?
Related to that, they give a class in January where they have a week of introducing their own concepts. If you try to do it in the spring, then it would be automatic. And then it's straightforward to teach them. But you don't have to know the program.
Okay, that's awesome. Thank you so much.
But this is the full strength version. So I've given you a very kind of big overview. It's not quite as sharp and crisp as what Greg Olson can do. He just knows this better than I do. There's just no way around that because he's been doing it for 40 years. He's really smart. So you'll, like I said, if you like this sort of thing, this is really good way to go take this class. It'll be real hands-on. You'll be designing your own material. It's a lot of fun. Okay, so that is the part of this course that involves materials. So we can now shift gears and talk about lightweighting via geometry, what I call geometrical synthesis. Synthesizing the dimensions of a part to meet its mechanical capabilities, maybe in terms of strength and stiffness. And then how do you do that at the lightest weight? Before I move on to that section, does anyone want to talk? Anyone have any questions about the material side of this? No?
You mentioned
Yeah.
the modulus, like saying something has the next modulus assumes that it has, so that is isotropic.
Right.
But that, like for anisotropic materials, it's okay to like have, or it's like, I forgot what it's called, but the same in one direction, but not in the other.
Orthotropic.
Yeah, no.
Yeah.
Is it still okay to see, like, the young modulus in one direction and then the young modulus in like the other direction?
Let's
Or
put
is that not common? Because like we made those kind of calculations in like one of the undergrad classes, but I don't know, is that like a common thing that's used? Like
Yeah,
in the industry?
it's almost like saying Band-Aid instead of bandage,
Okay.
right? Every Band-Aid is a bandage, but not every bandage is made by Band-Aid. Some are made by 3M, some are made by, I don't know, whoever else. Maybe in Germany there's Tessa makes those, I don't know. So it's one of these things that's really a technical fine point, and very few people will call you on it. Technically, you shouldn't do that, but I mean, no one's going to think you're stupid if you do. So I wouldn't get too hung up on it.
Oh.
But when I write papers or proposals or presentations, I'm always worried that somebody else is going to call me on it. So I'm always really careful to say like, no, these are elastic constants, and that's a Young's modulus, and they're not the same thing. Okay, any other materials questions? Anything at all? We know about ways to engineer materials for high strength, right? We know about ways to engineer materials for high stiffness. We know that there's these models out there that can take parameters of the microstructure like grain size, or precipitate population, precipitate size, distribution of sizes, morphology of grains and precipitates, and you can, in an ideal world, well, there are models that you can take those parameters and then calculate and predict a strength or a stiffness based on this. There's a couple computer models out there that will help you with that, like OOF, NIST. Okay, so that's the thing about materials. Don't always assume that you have to go to, the best thing to do is open up a book and look at the table with strengths and stiffnesses. If you need something better, ask for it. And a good materials engineer should be able to get you something better. If not, you can always hire Quest. Okay. All right. Okay, so now we're going to move on to the geometry part of this. Okay. Here we have two bicycle frames. Both of these are made out of steel. The green one was made in the mid to late 1970s, and the white one was about 2016 or 2020. It's a modern steel frame. Okay, the fork on the green one is steel. The fork on this one's actually carbon fiber, but don't worry about that. So the green frame, the steel from which it's made is a chrome moly steel. It has a tensile strength of about 800 megapascals. The white frame is also made from a alloy steel, except there's a sizable amount of niobium in there. Niobium is good because it reduces the grains. If I haven't told you that already, it's a good alloy element that allows you to reduce the size of the grains in a material, which is Hall Pett strengthening, right? And the material has chrome, moly, manganese, nickel. It's a multi-component alloy steel. The strength of this material is much stronger, 1250 megapascals, so 1.25 gigapascals, significantly stronger. The grain frame is made by brazing. So they have these things called lugs, which are sort of like a joint outline. Okay, they're made out of investment cast steel, typically, and they take the tubes and they put them in there and they heat it up with a acetylene torch. Right, they get the whole thing nice and juicy hot, and then they put a little bit of brass in there. Okay, and the brass melts really quickly, and because the spacing between the joint or the lug and the steel tube is so tight, capillary action sucks in the molten brass, and you get a really high strength joint by doing this. It looks great, makes a lot of sense from a mechanics standpoint, it makes a lot of sense from a material standpoint. The key to it is that you don't get it too hot. What happens if you get it too hot, guys? Go ahead. Well, it'll get weak. So you can grow the grains, so your Hall Pett strengthening goes down. You might grow your precipitates, you get coarsening. Okay, so it's not strong enough. The precipitates are past the optimal size, and the material goes down in strength. Okay, the white frame is actually TIG welded. So they just put electric current basically on there and get it really hot, put in a little bit of filler. And it's not quite as elegant as that, but I guess it works. The thinnest wall on these frames is in the center of the horizontal tube at the top there. We call it the top tube. From the center of that tube, that's where the wall thickness is the thinnest. In 1970, the thinnest they could get to was about 600 microns, 0.6 millimeters. Okay. In 2020, they can get to about 350 microns, 350.35 millimeters. So it's much smaller. Now here's where this is really important. The green frame weighs about 2 kilograms, and the white frame weighs about 1.6 kilograms. Interesting, huh? If you look at the tubes on the white frame, they're much bigger in diameter than the tubes on the green frame. So you have a combination of larger diameter, thinner wall thickness, which means essentially less volume of material. You're able to do that because the material is stronger and because the tubes are bigger diameter. So this is what I call strengthening by geometry. And of course, there's material strengthening here too, because the white frame is made out of much stronger material. But this is a demonstration of what you can achieve in, what is that, 50 years or 45 years? Okay, 45 years of development. Sophie?
So, like in regards to speed, like I know that the lighter weight of this frame will help the bike go faster.
Right.
But it's also like thicker, so how does it affect aerodynamics, or is it like?
Yeah. So there's
or is it way more important?
right. That's a tough question. There is an optimum solution, right? Yes, you do have bigger tubes, and those do hurt aerodynamics because drag is related to the frontal area times the coefficient of drag, right? So your cross-section area in the front is bigger. There's no way around that. If you do a lot of climbing, you probably will go faster by biasing towards weight rather than aerodynamics. Okay, because you're going much slower, you know, if you're climbing. If you're doing a lot of flat riding, you probably will do better focusing on aerodynamics over weight. So the bicycle industry has not only done an incredible job with structural optimization, both from the materials perspective and the geometry perspective, but they've also done an incredible job with aerodynamics. And the millions of dollars they're probably spending to rent out wind turbine or wind what do you call them, wind canals, wind tunnels, where they stick a bike in there with a bike rider on it, and they sculpt the tube so that they reduce the coefficient of drag. And of course, carbon fiber is a great material for that because it's very moldable. So you can get to all kinds of very intricate shapes. And they have done an incredible amount of coming up with their own cross sections and a D shape and a D cross section and so forth. So you're absolutely right. Both these things are important. I think, like I said, I think when you're climbing, it's really weight biased. When you're sort of on flats or descending a lot, it really becomes very aero based, right? Aerodynamic drag goes up with the speed squared. So, you think about descending at high speed or going on flats at 35 miles an hour in a big pack of riders. So that, anyway, does that answer the question? Okay. Yeah. So,
Oh,
Tyler.
I was wondering,
Sure.
I know it's in general, like larger diameter, like center wall tubes, is that like really bad for coupling failure?
Yeah, it can be. So this goes to what I talk about, off-axis loading, right? The closer you get to that optimum stiffness, that minimum weight, that perfect aero profile, the more the bike is, I think, specialized for one use, for one particular loading condition. You're right. The problem is off-axis loading. I'm sorry guys, sorry about that. If you crash in one of these on this bike, you're probably worse off than if you crash on that bike. If you lean the bike up against a tree, let's say, and something goes wrong, and suppose, I don't know, you put the handlebar on the tree or the telephone pole, and somehow the bike rolls forward, and then the top tube smacks into the tree or the telephone pole, you get a dent real easy, and your frame's ruined. So it's really all about what happens with off-axis loading. Okay, crashing. If you're just sitting there riding the bike, it's not going to fail. It's great. The second something goes berserk, like a tree or a crash or a dog runs out on the road, there's a good chance your frame is toast. So the lighter weight the frame, the bigger risk you're taking towards that catastrophic failure when it's loaded off axis. It could buckle, for example. And that's the thing I think a lot, you're trading off sort of multi-axial loading durability for performance. And I think this is, getting kind of off topic here a little bit. This is kind of a place where I think the bicycle industry they sort of live on an edge. Their customer is choosing one bike over another based on weight or some claimed aerodynamic advantage, right? And so the bike industry will constantly push towards, my bike only weighs 700 grams, or my bike only weighs 600 grams, or my bike only weighs 500 grams. So they're pushing that direction. But the second you get somebody who uses this bike, in some way that it wasn't meant for, right? Even putting it on the, the bicycle rack, and there's that little gripper that grips it, you put it on the tube and it crushes the tube. It's loaded off axis and it fails. So, and this gets into litigation and, yeah, I saw the frame, my carbon fiber frame had a little scrape on it. And I didn't think that much about it. I just rode it, then it failed, and now I'm a paraplegic. I'm suing Trek. So I think the bicycle industry needs it. In some sense, I think they need to do a better job of warning their customers that you can buy this bike, and yeah, it's only going to weigh 12 pounds, but if anything goes wrong, it's going to fail, and you might get hurt. So, if you really want to ride your bike every day and you're not racing for money, maybe you should buy this other bike over here that's a little more durable, even if it weighs 2 pounds more. You know what I'm saying? There's really an edge there. Like, what do you, and I think the bicycle industry is really kind of caught in the middle because everybody wants the bragging rights of a lighter bike, but they don't want to suffer if there's a durability issue.
Right, are these more for like racing and like more professional use, or these also like, this kind of thing also for consumer bike as well?
Consumer, yeah. Yeah, if you walk out on Mass Ave right now, you'll probably see some really high performance bikes eventually, some guy riding it down the street. There's a lot of riders around Cambridge, right? Also where I live in Dover, it's lots of bicycles all weekend long. You know, these older bikes, like the green one, a lot of those things are still riding around because they're very durable. There's a lot more extra meat there. They weigh a lot more, but they might survive a crash a lot better too. Just
Yeah, so as far as buffering.
Yeah.
I thought that the area or secondary movement direction is larger, so
Mhm.
your buffering condition requires greater force.
That's true.
So then like the thicker, even if it is thinner, when you have a wider diameter. I don't know.
Right, but it's that, like I said, it's that one time that the bike slides and hits a tree, and you get a little dent, and then it loses its buffering capability because there's a stress concentration there, and then when it gets loaded in some buffering condition later, it fails. It's like the military. I mean, they really push the limits of structural optimization and fighter jets and things like this. Okay, so modes of loading. Sounds like Christiane, sounds like you're know about this stuff. Good. What? Yeah, I was a mechanical engineer in grad too, but I still came across a lot of mechanical engineers who didn't know this stuff from my career. So these are the basic modes of loading. There's tension, there's compression, there's shear, okay, single shear versus double shear. There is 3-point bending, 4-point bending, there's torsion, and Christiane just mentioned there's buckling. These are the probably like the 5 basic modes of loading. The materials engineers in the room, I don't know if you guys got this sort of stuff as an undergrad. You did? Okay. And you're,
There's a question about the single shear and the double shear.
Yeah.
So, like the shear is so it's going like this, right?
Right.
And then the double shear, is that 2 different pieces or is it the same?
let me show you. Chalk there. Suppose you had an A-arm. Okay, this is a suspension component, right? And there's a hinge at the end. Okay, so if this is a car, you'd be looking downward on the car, plan view. Here's a control arm, right? So this is part of the suspension. This thing will articulate, like this, right? So the wheel sits here, the wheel moves up and down, this control arm, side view, here, here, here. Okay, it's articulating like this, right? If the body of the car is over here somewhere, right? If this is supported by a trunnion that looks like that, here's another one. Okay, so this is stationary with the car body. These two are stationary with the car body. This is double shear. If you take one of these away, you just have the control arm and this little tab sticking out with a bolt through it. That's single shear. You want to avoid this one because it introduces a larger bending moment. And then that's extra stress that has to be designed for more material, more weight, or else it maybe fails earlier. Make sense?
So is it just like it's double shear just because there are 2 of them there, so it's like double the shearing action?
Right, right. It's like you see, if you can imagine this one fitting in between those 2 mounts right there. That's double shear. There's less of a bending moment on this one. That is single shear. It's only versus this one.
Oh.
This is double shear. This is single shaded.
I get it. Okay, so it's the middle bar that's being, okay, I see. I was looking.
The blue one's being loaded up, yeah.
Gotcha.
Okay. Everyone see that? Don't forget to erase it, okay? Okay. Our friends in the mechanics department have long ago calculated out the stress and the stress distribution given these different modes of loading. In simple cases, if something's loaded in tension or compression, okay, the stress is dislinear with this dimension h. So the the dimension v would be into the page, and h is this dimension. Okay. This is just linear. If you hold v constant, the stress will go down linearly with h. As you go wider, the stress goes down. Just linearly with h. It's a linear relationship. When something's in bending, it gets more interesting. The stress actually goes down with the cube of h, assuming b is held constant. And this becomes a very powerful tool for lightweighting because of this cube relationship. Torsion is even better. If you have a tube in torsion, the stress goes down on the outer skin of this tube in tension with the radius to the fourth power. Important step. This is an important fundamental to remember. Everyone got it? Here is a graphic that I tried to put together to use some sort of gut feeling of what this means. Here are three different tubes in torsion, okay, with increasingly smaller radii. So if you start on this outside one, this blue one, okay, and you apply some torque to this, this little, what I tried to draw here in scale is a little vector on the end. I tried to magnify here so you can see. The length of this little vector is representative of the stress in the outer skin of this bar in torsion. If you then half the radius to the green one, the stress goes up from this little tiny thing right here to that thing there. And the length is representative of the stress. The longer the length, the higher the stress. If you then cut that in half again, so that the radius of the yellow one is 1/4 the radius of the blue one, this gigantic, yellow line right here, that's how big the stress is in the outer diameter. So for the same torsional load, as you decrease the diameter, the stress goes up very, very quickly on the outer skin. You can use this to your advantage in lightweight. This is what we just described with the white belt. Okay, rather than having one way to reduce weight while maintaining stiffness is to go to a larger diameter and a thinner wall thickness. So you have less volume of material in the bigger picture. That's reduced weight, right? Because density stays constant. But you have the same stiffness because you're taking advantage of the stress drop as you go to a larger diameter, right? So stress and strain go together, right? Always. Stress equals Young's modulus times strain, always. So in this case, we've got two different tubes, tube 1 and tube 2. They're both the same length. They're both subject to the same bending moment, and they're both made out of the same material, which means they have the same Young's modulus because it's isotropic. The tube 2 has a diameter that's 1.4 times larger than tube 1. Tube 2 has half the wall thickness as tube 1. For the same stiffness, tube 2 weighs 0.67 or 2/3 the weight of tube 1. Very effective. So you've maintained your stiffness, you've reduced weight by like 30-something%, right? Very effective way to reduce weight. And this is what they did in the white belt. I have an example I'm probably going to show you next lecture where I've done the same thing with torsion to show that how much weight you can drop when you make it bigger, make the diameter bigger, the outer diameter bigger, reduce the wall thickness. And I'll show you this next lecture. Based on these stress equations that I've shown here, I've derived what I call the constitutive laws for mass savings. Right, so this is if you have the same geometry part, but you substitute one material for another, and you maintain stiffness or strength. What is the potential for weight savings? Okay, so M is mass of a structure, rho is density, and sigma is stress. E is Young's modulus. So here's a derivation of the equations I just showed you on the previous page. Now you guys are good at algebra, you can figure this out on your own. But I just wanted to put this up there so you can see what this looks like. I need to get you guys a copy of this slide deck so you can look at this on your own. Yeah. So pretty much the way that I've done this is. Okay, I'll let you guys go through this on your own. Let's get just a copy of this. It's really easy. All you're doing is you're taking equations for the stress for two different structures made of different materials. You equate them together, then you solve for the ratio of the masses. It's pretty simple. So this comes up. You can go through this on your own. You guys are good at math. I'm sure you can figure this out. If you take table values, which you're not supposed to do as a materials engineer, but if you take table values, these are just uncontroversial or not controversial numbers. I just pulled these out of a, whatever, mechanics book, a journal paper, ASM guide, whatever it is. You take the values from those books and you start plugging them into these equations. It's interesting what you learn. Here we have numbers for carbon fiber, kind of normal garden variety carbon fiber with say a volume fraction of about 60% volume fraction fibers. Steel, magnesium, aluminum. It's a 6061 aluminum with a treated to a T6 condition. A T6 condition means that it's artificially aged. Fiberglass, so nothing fancy fiberglass, and then titanium. It's your garden variety 6-4 titanium, which is a very popular, say, like in fasteners. You start plugging these equations in. Okay, so you have on the far left there, you have the mode of loading. Then in the next column over, you have the design regime. So are you designing this part because it needs to be stiff, or are you designing this part because it needs to be strong? Which one of these requirements requires more material in order to meet? In a design for strength scenario, it means that you're adding material until the part meets a certain, the component reaches a certain load carrying capability. If you're designing for stiffness, you're adding material, like wall thickness, for example, or diameter, cross section. You're adding that material in order to get a certain stiffness. So when you put an elephant on the end of a beam or a diving board, how far does the diving board flex? So that would be an example of a stiffness requirement. Okay, you start, and then the constitutive laws, okay, for both of those different design regimes. And then here's a ranking when you start plugging in those different materials values, the values you get out. And the thing I think the most important thing of all this that I want you to take away from it, you can go through this and it's fun to look at this stuff. You can even start plugging in your own materials like beryllium. The most interesting thing is that in a design for stiffness scenario, okay, when you're designing, you have linear loading like a tension or a compression. In a design for stiffness scenario, steel, you can make a lighter structure from steel than magnesium, aluminum, titanium, and fiberglass under that single scenario. Think about that for a second. A lot of people, companies, engineers will take expensive materials like titanium or carbon fiber, and they will expect to get a big weight savings compared to their steel cousin. And then it doesn't happen because steel has a really high Young's modulus relative to its density. And because of this, you can make a structure sometimes it's stiffer with steel for a given weight than you can out of those other materials because it has such a high Young's modulus. This is kind of surprising to a lot of people. People just figure, well, you make it from aluminum, it's got to be light. But it depends what you're making. The other assumption that's embedded in here is that you have all the packaging space you need, which isn't always the case. So the example I always like to give is the side intrusion beam on a car. You have Suppose you have a, what's this? Suppose you have a door. Okay, there's a door in a car, there's a door handle, right? There's actually a beam that goes like that. That is meant to stop other cars from getting in your car to get hit in the side, so it doesn't end up in your lap. And if you look at a cross section of this door, you have the outer skin, you have the window inside of it. You might have a trim panel made out of cloth or leather or something nice. And then right here you have a side intrusion beam. That's this piece here. You don't have infinite space in order to make this thing a bigger diameter. It's almost similar to what you were saying about the arrow. Like what's more important, arrow or strength? You don't have infinite area to make this as big as you want, right? So this is a situation where this is actually designed for strength, right? Because ultimate strength is you want to keep another car from getting inside your car, right? But you can't make this thing infinitely big. So if you made this part from aluminum, yeah, you might be able to get sufficient strength out of it. But you have to make it very, very, very big in diameter. You wouldn't be able to package it inside the door. You make your customers really angry at you because they wouldn't have any elbow room, right? They wouldn't buy your car. So this shows you like packaging space is really critical in choosing materials. You have infinite packaging space, and you have these different scenarios here like bending, design bending or torsion or buckling. Yeah, you can make a lighter structure out of aluminum if you have infinite packaging space. So remember that. Always ask yourself, how much packaging space do I have? And that can help you decide which material makes the most sense. Any questions on that one? I'll ask Professor Eager how to make this available to all of you, and you can go ahead and you can look at these various numbers of percent weight savings. Another important thing here is that the carbon fiber, assuming at room temperature operation, carbon fiber is really amazing. Just the fibers themselves are incredibly stiff and incredibly strong. And under any of these loading scenarios, loading types, regimes, you really can't do better than carbon fiber if you have the money, if you have room temperature and you have the money to buy the carbon fiber. Okay, percent.
Are these carbon fiber really in epoxy or what?
Yeah, that was in here. So this is carbon fiber epoxy, 70% volume fraction. I've made the assumption that that these are isotropic properties, which they're not, but just to make calculations easy. Okay. Any questions on this, guys? So here's an example. You have a roof panel on a car. A roof panel doesn't do much as far as the strength or stiffness it imparts to the car body. The roof panel is typically very thin when they're made of steel, like 600 microns, even on a Toyota Corolla, a very common car. What material would you choose for that? Knowing that it's imparting very little, it's not doing any very little structural job. And cost is important. Any thoughts? If you look at some upper end German cars, for example, you'll see that they put carbon fiber roofs on some of them, and it looks cool. But because the carbon fiber really isn't doing much other than just keeping wind and water out of the inside of the car, it's not saving you much weight to do that. I always used to say that Chrysler, if they could make waterproof cardboard, they would use it. Because some panels on a car don't do anything other than keep wind and water, yet you substitute very high mechanical capability materials into those applications, and you're spending a lot of money, but it's not really doing much. So just be wary of that scenario. All right. Here's some more examples under different loading conditions. Buckling, your favorite one, Christian. You go back and look at that. These are what are known as Ashby plots. I guess most of you guys have probably seen this. So these Ashby plots are really nothing different than what I just showed you, except they're much more fun to look at. This is basically just a plot of those constitutive laws for weight savings that Ashby has done, Michael Ashby did. he has these, what they call these, materials index number, M, right? And you want to maximize these under the different modes of loading, different design regimes in order to maximize weight savings. And those are these parallel lines here. So these are fun to look at. We got 5 more minutes. Here is a car body, right? Made out of steel stampings. Okay, it's very easy to then, or not easy. It's readily possible to think about this body structure, no matter how complicated it might look in that picture. There's a series of beams, hollow beams that are under different loading conditions, right? There are front bumper. I'll just go through a couple. There's front bumper, right? There's this rail structure here, both right and left. There's these rocker tubes, rocker panels. There are rear rails, rear bumper. There is what's called the A, B, and C pillar. So the A pillar is the one that's like, if you're sitting in your car, it's like the one that's right here. And the B pillar is the one that's next to your shoulder. And then the C pillar might be if you have someone sitting in the rear seat, it would be next to their shoulder, right? There's a roof rail that connects those pillars. Then there are cross members in between. There's a structural member that goes sort of where the sun visors are. There's a structural member that connects the B pillars, called the roof bow. And then there's the rear cross member that connects sort of above the rear window, right? There's inner rails. There's this seat cross member. There's a tire tub cross member. There's this right here that is next to the dash panel. It goes cross car. There's a cowl cross member, which sort of goes to the base of the A pillars across the car. These are some examples of different structural members that are in a car body. You can start to think of a car body as being made up of these different structural members. For different loading conditions, front impact, rear impact, global torsion, so take the body and twist it, global bending, take the car and bend it. It's possible via intuition and via finite element analysis to determine the mode of loading on each of these different structural members. Once you know that, it becomes very clear which members are worth spending money on to use exotic materials like aluminum or magnesium, and which ones you're not going to do that much. You're not going to get that much benefit. You might as well just use steel. For example, these roof header, roof bows, so these cross members that go into compression only when the car's loaded in side impact, for example. They really only ever see a compression load. Okay, so because of that, you can often do better with a steel part than an aluminum part or carbon fiber part. Well, not carbon fiber, sorry, a magnesium part. To make a lighter structure with steel, or at least a cost competitive structure that's lightweight with steel compared to making it out of aluminum or magnesium or titanium or something like that. Other members like front rails. Well, that's probably not a good example. There are these other components here that have mixed mode loading. They see bending, they see torsion, they see tensile. Those are the materials where you can do better with aluminum. You can create a lighter structure from aluminum. The Audi TT, the most recent generation Audi TT thing, you guys know that car? I guess it's getting to be kind of old, you know. I guess that car came out 20 years ago. The second generation of that car, they used what's called a mixed material solution, where they basically followed this strategy right here. Cross members were made of steel. I'm sorry, cross members, think of that. Longitudinal members were made out of aluminum. Some cross members were made out of steel. And then they used steel for closeout panels because they didn't, you know, it's cheap, doesn't need much. But they used the exotic materials where they do the most good, like in rail structures and B pillars and A pillars, things like that, that are under sort of bending rather than just a compression or tensile. So start thinking about like things around you and how they're loaded. And if it's only seeing a compressive load or tensile load or shear load, you could probably be pretty competitive from a weight perspective. at a low cost using steel. If you see members that are under bending, buckling, torsion, you can make a lighter structure out of aluminum or magnesium or titanium. It comes down to this specific property, the strength to density and the stiffness to density. Okay, so next time, when you guys come back with some thoughts on some things you see around you and how they're loaded, and whether it would be lighter made out of aluminum or steel. Tyler, good question?
So I was a bit confused about the table here.
Sure.
Like, let's say like we're better has some like compression in the torsion column.
Right, so this was, this table I derived when I was at Chrysler a long time ago. And I was looking at, a finite element result in torsion. That's what I started in the question. It's not always intuitive how these things are loaded. Sometimes it is. Sometimes you're only really going to get to the answer by using a finite element analysis.
So it's if you put it in torsion, you can see the load.
Pretty much,
Or
yeah.
you have to put a compressive load on it to see torsion.
So,
Or is it the other way? Like, which one's like the applied, which one's the result?
the applied is the global load.
Okay.
Okay. Portion, and this was described right here. I was kind of rushing to go through this very carefully, but the way that they measure torsion stress, or car companies will measure the torsional stiffness of a body structure. And what they do is they grab it by the suspension mounting points and they twist.
Oh, this is like the entire car.
This is the entire car body, yeah.
Okay.
Global loading, they twist. They work on bending loads, but actually put a beam across like the front seats, basically, or where the front seats would be. And they hold the car fixed by the shock, by the suspension, like shock tower, for example, and they push down. That's how they measure bending. And then they have different dynamic versions of that too, where they sort of hit it and measure the natural frequency. Okay.
So how important is the global coordinator? Imagine it's like an off-road vehicle, the car would see a lot of different things from it. It's like a normal car. Really.
You feel torsion loads when you're cornering.
Okay.
Or I should say, you feel the effects of torsional stiffness when you're cornering. It has to do with the way the car responds when you turn into a corner. If there's a lot of movement there, you turn the steering wheel, you sort of have a vague feeling of where the car might end up.
Yeah.
When they're very stiff, it's much more, it does what you expect it to do much more likely. So just to give you guys an idea. So Formula One cars in like the 1960s would have a torsional stiffness of like 5,000 or 6,000 Newton meters per degree of twist, right? Modern Formula One cars have about 60,000 Newton meters per degree. Much different. A good sedan, like a Mercedes, I happen to know these numbers, for example, like a C-Class Mercedes is around 27,000 Newton meters per degree. Just to kind of give you a range of where these things hit. The Dodge Neon's about 11,000 Newton meters per degree. It's very complicated. It's a dynamic system. You're dealing with vibration, noise from vibration, feelings of security and lack of security. Okay, and there's static properties and there's dynamic properties. And all these things go into, when you sit in the car and you're driving, you feel like you're going to crash and you feel like it's safe. But the car companies obsess about these things, to be honest, especially Mercedes. Julian, any questions? No? Okay, great. See you guys next week. Start thinking about loading conditions. Give me an example next week of how something's loaded and whether you would make it out of steel or aluminum to get lightweight, okay?
Like asking plots. It's like all roads always lead to carbon fiber unless